Lesson 1.4, Day 2, has us using information about quadratic functions and graphing using a variety of methods. In this lesson, we'll look at 3 different types of quadratic functions and the key features needed to graph them. We'll start with the most common function in standard form. Standard form is of the model y equals ax squared plus bx plus c. And we've factored this, we've solved this. Now we'll look at what's needed to graph this. So underneath, we're going to write all the key features for each form. We'll have a lot of commonalities, but different ways to get them. For quadratic functions, you're going to want to graph the vertex, which is kind of like the turning point. In standard form, to get the vertex, we just follow a formula definition. X equals negative b over 2a. Using the coefficients from the equation, that will give you the x-coordinate of the vertex. To get the y value, you just plug x into the equation and simplify. That ordered pair will be your vertex. And that's the most amount of work. The rest of it should be pretty easy. From here, we'll draw in what's called the axis of symmetry. The axis of symmetry is a vertical line that pretty much just cuts the quadratic function in half, right down the middle, so that the left side is the same as the right side. When you know the vertex, the axis of symmetry is an equation modeled by x equals h. And h is just the x-coordinate of the vertex. So whatever that x-coordinate is, that's what your axis of symmetry will be. And then you draw that dotted line right through the middle at that location. The y-intercept should be pretty easy to find. Usually we let x equal 0. But if you look at standard form, once x equals 0, the first 2 terms cancel out. And you're left with that constant at the end of c. That's the y-intercept. Once you have the y-intercept, what you'll want to do is just reflect that point, there we go, over the axis of symmetry. And then that'll give you kind of the boundary for the curve that creates your quadratic function. Next, let's talk about vertex form. There's lots to say about vertex form, so I had to give myself a little bit more space. Now, vertex form is still quadratic, but it's going to look different than standard form. When you have a quadratic function in vertex form, you're still going to have that lead coefficient of a, but now you're going to have x minus h in parentheses, and that entire parentheses is going to be squared. And then you have plus k on the end. And if you remember from Algebra 2, if you took it last year, that this is just a translation of the parent function. So it just is kind of modeling what the parent function for a quadratic would look like. And now the vertex is actually really easy. There's no work for the vertex on this one, so it's nice. The vertex is always whatever h is in that equation, and then whatever k is on the outside. And that's it. It's that simple. Once you have that, your axis of symmetry is again x equals h. It has to be written as an equation, and that's that dotted vertical line. Here's where the work will come in. To find the y-intercept this time, now there's going to be work. It's not just 0, k, because k is part of the vertex. We have to plug in x equals 0 to the equation and simplify. And that will give you the y-intercept. And then just like standard form, we'll reflect that over our axis of symmetry. And then you should have enough information to draw the sketch for your quadratic function. Last but not least, we have what's known as factored form. And giving myself just a little bit more room. Now, factored form is going to pretty much look like what we've been doing even back in time in Chapter P and what we just did in yesterday's lesson. Factored form takes the model y equals, we still have a lead coefficient, but now will be factored. So we have an x minus p and x minus q. So make sure you can recognize the difference between the three forms. In this form, we actually don't calculate the vertex till the end. What we'll do here is get our x-intercepts. And x-intercepts are formed by setting the parentheses equal to 0. So x will equal p and x will equal q. As ordered pairs, that's p comma 0 and q comma 0. And you plot those on the x-axis. Now to get the vertex is going to be right in the middle because quadratic functions have symmetry. So to get the vertex, your x-coordinate is going to be found by taking the average of the x-intercepts. We'll take p plus q and divide it by 2. And that'll be right in the middle, and that's the coordinate for x for the vertex. Like standard form, to get y, we'll plug x in and simplify. And that should be, again, the most amount of work that we have to do. From here, then it's kind of business as usual. You get your axis of symmetry. And again, that's x equals h, the same as it's been the whole time. And then the nice thing about this, since you already have your x-intercepts plotted, the y-intercept is optional. Because you'd have to plug in x equals 0 and simplify. So if you don't feel you have enough points, you could plot that one and then reflect it as another set for your graph. These steps should be able to give you all the information you need to sketch the graph of a quadratic function. However, if there's a situation where the points you have don't fit your graph or you feel like you don't have enough, the alternative would be to always make a table. And you wouldn't have to plot a bunch of points, but just enough to give you that general shape for your quadratic function. So let's practice a couple. For each equation, determine the form it's in. Then state the key features and sketch the graph. Looking at example A, f of x equals x squared minus 6x plus 10. It's in the form where x squared is first, x is second, and the constant is third. This is known as standard form. We'll follow the process in that first column to sketch the graph. The first thing we want to do is find the vertex. And that's kind of that turning point for that quadratic function. To get the x-coordinate, we follow the formula negative b over 2 times a. b equals negative 6. That's the coefficient in front of x. That gives us a double negative. We'll have to be careful for that. A is technically the number in front of x squared, which equals 1. If there's not a number there, it just defaults to 1. We have a double negative, 6 over 2, which equals 3. The x-coordinate of the vertex is 3. To get the y-coordinate, we'll plug that into our equation. We have x squared, so I'll plug in 3 and square it. Oops, let's make sure that's easier to see. There we go. Minus 6 times 3 plus 10. And now we just simplify. 3 squared is 9. 6 times 3 is 18 plus 10. 9 minus 18 plus 10 is 1. That means your vertex is the ordered pair 3, 1. And again, that's the most amount of work you'll have for this whole problem. The rest of it just kind of comes from this information or the equation itself. The next step is that axis of symmetry. And you don't have to do any work for that. Oops, that's except for writing your letter M correctly. Yeah, you know, details. There we go. Now remember, the axis of symmetry is always found by the x-coordinate of the vertex. X equals 3 is going to be the dotted vertical line that we graph when we get to that point. Our y-intercept comes from your equation. It's just the value of that constant. The constant is 10. Therefore, 0, 10 is where it crosses the y-axis. Let's go to our graph. First, plot the vertex over 3 up 1. There's the vertex for our quadratic function. That'll be the turning point. We'll graph the axis of symmetry next, and that's that dotted vertical line that just goes right through it. Do you guys remember doing that last year in Algebra 2? Hopefully you do. So we'll draw that from top to bottom. Then we'll plot the y-intercept 0, 10, so that's all the way up at the top. And then we reflect that point, whoa, hey, there we go. We reflect that to the other side. If the y-intercept is 3 units away from that axis of symmetry, I'm just going to go 3 units on the other side. So do you see how on the left and then down at the bottom where that vertex is, and on the right, see if you can draw a curve through those 3 points. Hopefully your quadratic function looks something like this. Make sure to have arrows at the top. Clearly, we're having a lot of fun. So let's go ahead and try just one more for the video. Take a look at the form this is. Can you identify the type of quadratic function? With one parenthesis being squared, this is known as vertex form. And because of that, we'll follow the steps in the middle of our table up above. Now remember, vertex form means the vertex is going to be the easy part. So we'll take that when we can. Now the value on the inside is always the opposite sign of what it says in the equation. If it's x plus 3, that means the x-coordinate of the vertex is actually -3. And then whatever's on the outside is the same. So it stays +4. And that's it. There's no work after that for the vertex. Your axis of symmetry, also a freebie. Remember, it's always the same as the x-coordinate of the vertex. So we're going to match that number right there. And that'll be our dotted vertical line when we're done. Here comes the work part. To get the y-intercept this time, we have to plug in x equals 0. It's not just that 4 on the right. So we're going to have to do some work here. If we plug in 0 for x, now we have to simplify. Thinking order of operations, the parenthesis 0 plus 3 is 3. 3 squared, oh boy, is 9. -2 times 9 is -18. And if we add 4 to that, it's all the way down to -14. The y-intercept then is 0, -14. That's not really user-friendly for our table because it only goes down to -11. So remember what we said, if you're graphing and you don't have enough points, what we're going to do now is just make a table. And I know it sounds like a lot, but it really won't take us long to get enough points to plot. So I'm going to make my table, and what I'm going to do is actually take the vertex and bring it right down here and plug it in on the left side and the right side. And if I graph the vertex, -3 up 4, what I want to do is just pick values for x that are close to -3. Honestly, something like -2. Now if I plug -2 into the equation, y will equal -2 times -2 plus 3 squared plus 4. And we just have to clean that up. -2 plus 3 is 1. 1 squared is also 1. 1 times -2 is -2. Plus 4 equals 2. That means the y-coordinate that matches is just 2. So I'm going to now draw the axis of symmetry. We probably could have done that before. Just going to draw that in, and then we'll start doing some reflecting to see how many points make sense for us to graph our quadratic function. -2, 2, and I'm going to reflect that to the other side. Let's go ahead and pick one more. Let's plug in -1 and see what we get. -1 plus 3, and then we'll square that. So -1 plus 3 is 2. 2 squared is 4. -2 times 4 is -8. And -8 plus 4 is -4. I think we're going to be good now. If we plot -1, -4, and then reflect that to the other side, are you seeing that curve start to take shape? And now it's opening upside down. Go ahead and sketch that quadrant. And there you have it. Now there's a reason that this one kind of looks a little bit more narrow than the others, or than the other one that we saw. And we'll talk about that tomorrow in class.